Hello, I'm Nicolas Krauter, and welcome to our presentation on persistent software transactional memory in Haskell. In recent years, persistent memories, which are also called non-volatile main memories, have been gaining traction. They fill the gap between storage and DRAM with their unique characteristics. They are byte addressable, offer latencies comparable to volatile memory, and are a viable candidate for mass long-term storage due to their large capacities and persistent properties. From the application's perspective, persistent memory can be used in the most performant way using its direct access mode, where it's mapped directly into the application's address space. However, this has many new challenges for the application developer that were previously externalized to a file system or a database. The right-hand side shows an example of the modification of a FIFO queue through the API of Intel Persistent Memory Development Kit, also called PMDK, which tries to reduce the complexity of programming for persistent memory. However, there are still many new obstacles that need to be handled manually. First, the persistent memory region needs to be explicitly mapped into the application's address space. The access to all data structures needs to be ensured at all times, and atomicity needs to be expressed correctly. Here, PMDK uses the well-established persistent memory transaction semantics. However, in this case, the application developer still needs to ensure that the transaction cannot be breached, as mutating global state outside of the transaction is still possible. Additionally, data needs to be explicitly allocated, and referential integrity needs to be ensured at all times. This includes the correct and explicit management of lifetimes of reference structures, as well as that no transient structures are referenced that would be lost across the application runs. When using any kind of multi-threading, this example would get even more complex for PMDK, as the application developer would need to handle this additionally, as the library does not manage any of it in the background. We analyzed many existing solutions written in C, C++, Java, Go, and so on. While they offer some kind of alleviation through high abstractions such as concurrency guarantees and automatic memory management, they still allow for some kind of inconsistent usage of persistent memory. For example, they cannot transparently avoid assignment of volatile structures. We argue that for languages with such a low memory abstraction that offer arbitrary byte or field level access, there's always going to be some kind of trade-off, as the imperative language model itself is the problem. It is not restrictive enough, as arbitrary modifications are allowed, which result in large overheads when traced by the runtime system. Thus, PM cannot be safely integrated into these languages as an afterthought. So we asked the question, can we design a system that ticks all boxes, that handles all the challenges discussed previously in the background without the application developer needing to worry about it? And we found that with their limited mutability, purely functional languages are exactly the right paradigm, as they offer the right constraints to build very transparent abstractions when working with PM. We can design specific solutions for the limited set of mutating operations that are available in the language. As a proof of concept, we modified the Glasgow Haskell compiler that didn't know anything about persistent memory before. We integrated our solution into the runtime system of the language to support persistent memory as a first principle. For this, we designed a hybrid heap that is persistent across runs and directly extends the volatile heap by mapping it into the application's address space. We use a fixed mapping that's handled transparently by the runtime system to ensure the integrity of references in PM across runs. And we only store native closure objects in persistent memory to allow direct access at any point without serialization or deserialization. As we are fully integrated into the memory management of the language, we provide garbage collection of PM through a reachability-based mark and sweep collector that is based on the recently introduced Alligator garbage collector found in GHC 8.10. Also, we integrated a PM-tailored allocator design that uses minimal logging and is specifically designed for Haskell closures. To interact with persistent memory objects, we chose to use the well-established persistent memory transaction semantics. For this, we extended Haskell's implementation of software transactional memory, which is very well integrated and used by many application developers to ensure the concurrency-safe modification of specific mutable variables called TVARs. we introduce PTVARs as a direct persistent counterpart to those volatile TVARs. In our system, which we call PSTM, PTVARs can be created and modified with the functions new PTVAR, write PTVAR, and read PTVAR. For those of you that are familiar with the original STM interface, they strongly resemble the operations offered for TVARs. Additionally, we use a persistent programming concept called the persistent root that allows you to gain access to the persistent memory structures across runs. We provide the root as a unique PTVAR variable that can be obtained through the getRoot function. Using the passed argument, the value of the root is initialized on the first call to the function. All subsequent calls to the function return the current value and ignore the passed argument. As we are using the STM monad, we still allow TVARs and PTVARs to be modified jointly so that volatile and persistent data can be modified in one single and power-fail-safe atomic transaction. To get a better feeling for our system, we'll show you a couple of examples now. When you want to access the persistent structures, you would call getRoot. In this example, it returns a list of PTVAR ints. The type of the persistent structure is determined by the initially passed value. We allow arbitrary PTVAR values so that you can have very complex structures that are stored without serialization in persistent memory. Also, what you can see here in this example is a direct reference X to a PTVAR that is not reachable from the unique root. This is fully supported, and the PTVAR functions as a volatile heap extension that is collected across runs automatically as it's not available from the root, and this structure is only referenced through the volatile heap, which doesn't exist in the next run anymore. In fact, a memory structure is alive as long as it's referenced from either the volatile heap or has a transitive connection to the root PTVAR. Transient PTVARs can be used in scenarios where PM needs to be used as a volatile heap extension, as PM has much larger capacities than DRAMs. In this example, you can see how PTVARs can be jointly modified. Currently, there is X and Y in persistent memory, which we modify through the transaction, which you can see on the left. We first read them and then we add 5 to each one of them. So then only when STM ensures that the variables can be committed without any concurrency issues, there do we copy the data over to persistent memory. Then we use minimal logging to perform atomic pointer updates to ensure power fail-safe execution. We do not need to log anything else, as our automatic memory management will take care of collecting any leftover data in the next run. Finally, Z is returned as a direct reference into the persistent memory heap, which can be used as any other Haskell expression. As our system is fully integrated into the language's runtime system, we can also support the lazy execution model of Haskell in order to offer an idiomatic language abstraction. So developers can store arbitrary functions and unevaluated expressions in PM. In this example here, we can see that X points to the expression y plus 5 with the environment y equals 1 in PM. In case that X is evaluated, any intermediate results will be created in the volatile heap first. While this is shown here with the integer addition, more complex intermediate results can contain unevaluated sub-expressions themselves. These then would be computed in volatile DRAM as needed, and only the final result would then be copied over to PM. Finally, the result pointer is updated consistently by using atomic pointer updates. Being fully compatible with the lazy execution model allows us to use many existing libraries that have never heard of persistent memory before. Here in this example, we use memoization libraries to create a memoized version of the Fibonacci function. By persisting and retrieving the memoized function, we obtain the persistent memoized function that internally tracks all previously computed Fibonacci numbers in PM. In this case here, the fixed point memoization not only stores the final result of a function application, but also all required sub-results. And this happens all transparently. In our benchmarks, we saw that for the memoizing of the first 150,000 Fibonacci numbers, we have an overhead of 4 to 5x when storing it persistently on Intel's obtained DC persistent memory versus the volatile counterpart. However, now you can amortize this overhead across multiple runs and not just the current run. Finally, let us look at a comparison of PSTM with other persistent transaction libraries out there. We here show the results of red-black tree and hash table benchmarks. However, we have more in our paper. We analyzed the libraries OneFile, Romulus, PMDK, Mnemosiny, and compared it with our system. There is 3 possible operations that we perform on the data structures, either lookup or insert or delete with equal probability. The x-axis of the figures show the lookup rate, which is the percentage of transactions that only perform lookups, thus only do reads on the data structure. The y-axis is the transactions performed per second. So let's first look at the other libraries independent from our solution. We observed that for the analyzed data structures, the top solution is not consistent. For RB tree, the rebalancing introduced by updates of the structures can lead to updates of many variables that introduce many conflicts during transactions. Here, Mnemosiny shows similar performance to our solution as it relies on a STM-like mechanism for concurrency control, while libraries such as OneFile and Romulus have high performance impacts as they do not allow for concurrent execution of write transactions. Hashtable, on the other hand, shows a different behavior. As it's a flat data structure and only few variables are being modified during insert or delete, the write transactions are sufficiently small and thus create much less blocking, thus leading to a higher performance of Romulus and OneFile. Mnemosiny's transactions are more heavyweight due to transaction logging overheads. However, we saw that PSTM shows very competitive performance to all other libraries. Note that we report 2 different configurations of PSTM, a blocking and an unlimited version. In the blocking configuration, we enforce a small size-limited heap to allow for fair comparison with the libraries that also reclaim obsolete objects in a timely fashion. The unlimited configuration is meant to serve as an upper bound for more optimized garbage collection schemes, as our garbage collector is not yet optimized for blocking collection phases where it does not benefit from possible multi-threading. In both configurations, PSTM heavily benefits from low logging overheads and STM's excellent optimistic concurrency control, which makes it a viable and performant alternative to existing libraries that provide less abstraction. In conclusion, we can say that persistent memory is a very interesting new technology that can be used to access persistent data without any kind of serialization or deserialization. We showed you PSTM, a simple API extension that allows even novices to write persistent memory programs, as it hides pretty much all the details of the technology while preserving its high-performance access advantages. We think that the language level constraints, such as limited mutability, here make building concise and comprehensible abstractions possible. The runtime integration of PM resulted in a system that allows idiomatic Haskell to be used to interact with the new technology. As our design is compatible with lazy evaluation, adaptation of legacy code is trivial, which is in stark contrast to other approaches that can require large rewrites of code bases when introducing persistent memory. Thank you for your attention. Please feel free to ask any questions to us via email or in the discussion section of the conference.